This is a lesson on how to graph linear functions and find their intersections, and I chose problems from Kinematics. So we're looking at rate problems, and you can see that in the first problem here, a walk in the neighborhood. It says you and your friend are walking back to your place after a stroll through the neighborhood. You notice your walking pace is 2 miles per hour and that you are half a mile away from home. The question asks, develop an equation in proper function notation as a function of time for your location relative to home. Clearly define your symbols. Okay, so we want an equation in proper function notation, and we need to define our symbols here. And it says we want a location as a function of time. So right away, I know I'm going to have a t value, and this is time. And in my equation, this will be sort of like the x value, the input value. And when I put in the input value, what I get is an output value. So a lot of times we will represent this as x as a distance. And so x will be the distance away from home. And so that's what I mean by clearly define your symbols, is whatever symbols you're using in your equation, it's clearly defined so that anybody reading your work knows what those symbols mean. So when I put this together, when I read what's going on in the problem, I see that we have a rate, a velocity or speed is the rate, and this will be the slope of my line. And we also have an initial value. Notice that we are half a mile away from home to begin with. So relative to home, we have a half mile to go. If we drew this maybe on a line, a coordinate system here, where this is displacement, home is here, here's home, and I'll say that x equals 0, and you start half a mile away, 0.5. Okay, so when we write out this equation in proper function of notation, I have a location as a function of time, so where you are is a function of time. At time equals 0, you're half a mile away, and then you'll go 2 miles per hour for each hour that you've traveled, and the initial value, the sort of y-intercept, the b value for this problem is 0.5. So when I ask for an equation in proper function notation, notice I have the input variable that's defined, I have the output variable that's defined, and we're going to write it in proper function notation. This is the location, distance as a function of time, and then that's the equation for it. So that's the answer for part A. That's all I want for part A. Then it says algebraically solve for how long it will take you to walk home at this pace. Well, algebraically, I can do a graph on this, or I can think about it, but I want you to solve with algebra. So that means writing an algebraic equation down and solving for a variable. I'm going to notice that at home, the position of home, x equals 0. So actually, I'm going to write out this equation. 0 equals 2t plus 0.5. And I'm looking at this equation. I'm not very satisfied with it. All right, because when I solve for t, notice that if I solve for t, I'm going to isolate this term on one side, so I get negative 0.5 equals 2t. And when I solve for time, I get a negative 1/2 divided by 2, 0.5 divided by 2, so that means t equals a negative 0.25 hours, which is 15 minutes. But I have a negative sign here, and I'm not okay with that. And that comes into the idea that I have to take into account the slope of that rate. Because I'm going towards home, it's in the opposite direction of the displacement, right? I'm moving towards home, so this is 2 in this direction, which is in the negative direction. So I should have a negative sign here on the slope. I'm going to add it in here, and notice that's going to make my time turn out positive all the way through here, and I get a positive value for time, which I expect. And that's the value that I would put a box around for part B here, is this time down here. Okay, so that's the two answers for part A and part B. Part C wants us to graph. It says use a graphing application, graph your equation from part A and verify your solution for part B. And that's why I have Desmos over here. You may also use Symbolab. I'm okay if you use Symbolab or any other graphing application to graph. I'm comfortable with Desmos, and I'm going to show you how to use Desmos here. Notice in my original equation, I have x and t are my output and input variables, but when I enter this into Desmos, Desmos doesn't think in terms of time. When I enter t, it doesn't automatically know that I mean time. And so what I'm going to do is use regular x and y for input variables and output variables in Desmos. So when I write this equation in Desmos, I'm going to say y equals negative 2x plus 0.5, okay, and 0.5. Okay, now that I have the typo out of the way, you can see that I'm getting this line drawn in here. But I can't really distinguish these. What you want to do, and I will often put this on instructions, is to change the scaling so that you can see the graph better. You can see the details of the graph better. So I'm going to zoom in here. You can use the zoom in function over here on the right side of Desmos. And you can move the graph around, and you can see that I start a half a mile away from home. And then when I get to home, the time that has passed is 0.25 hours, and you can see that on here. So you may want to do that is make note of the two x and y intercepts. But what it asks here is verify your solution for part B. So what I'm really interested in is this point here. When the displacement equals 0, I solved algebraically for the time is 0.25 hours, which is 15 minutes. And what I can do is on the graph, click that value on the point that I'm looking at here. I'm not labeling it. I have had students who like to label it over here, like they'll just label 0.25 comma 0 and click a label here. To me, that's not letting the application do what it does. And by that I mean, let me get rid of this, is when I click this line and I click here, I can see clearly that intersection. What I did was I set the displacement equal to 0, and I'm finding the intersection between this line that I'm looking for, right? On my work over here, I said x equals 0, the output variable equals 0, and so that's what I'm graphing on Desmos. The output variable is equal to 0. Where it intersects my original function is the intersection, and here I am verifying my point. Notice I'm not labeling it with Desmos, but I'm clicking on this point and letting Desmos tell me what that value is. So Desmos did an independent calculation, and it's verifying what I did to find my calculation. My calculation aligns with the calculation that Desmos did. If you use the label function over here like I did like this, I will not give you credit for that. That is not what I'm asking you to do, is to label this point. That's not what I'm asking you to do. I'm asking you to verify your solution, which means finding an intersection between two lines. So that's what you should do when you're working on your homework. I chose another example just to get another application going here. And what I have is two lines intersecting. You're going to see that here. Here we have the tourist and the bear. It says, I'm very fond of this problem. I think it's an interesting one that exemplifies what intersecting lines do, as well as function notation, writing equations, and finding that intersection. It says a tourist is being chased by an angry bear, and they're running in a straight line towards the tourist car. The tourist is running at a speed of 4.5 meters per second. The bear is 56 meters behind the tourist and running at 8 meters per second. So I'm going to do kind of what I did before on the previous problem. I'm going to draw a coordinate system here, positive x direction, and I'm going to let the car be here. Here's the car, and I don't know where the car is. I'm not going to let it be at the origin. What I will put at the origin is maybe the bear. Maybe the bear is at the origin. It says, write a linear equation in proper function notation for the position each of the bear and the tourist. Be sure to assign and define meaningful symbols to the variables and clearly designate who begins at 0 distance. So I'm going to let the bear begin at 0 distance. I'm going to let this be the origin. So that means that the tourist is here. Here's the tourist. And the tourist is 56 meters ahead of the bear, okay? So I'm going to let x be the distance. I'm going to have x of the tourist. So this is the position of the tourist. And I'm going to have x for the bear. This is the position of the bear. And I'm going to have a time variable. This is a rate and time. This is linear. They're both moving at a constant speed. You can see they're both moving at a constant speed. So when I think about the position of the tourist from the origin here, from the bear, okay, the position of the tourist as a function of time is going to equal 4.5 times time plus 56. He's 56 meters ahead of the bear. As opposed to the bear starts at the origin, so it has no initial value, and it is moving at 8 meters per second. So that's the equation for the tourist, and that is the equation for the bear. You wouldn't necessarily need to include the plus 0 on the end, but I do, just to be explicit for you, on your homework or anything like that, this much of the equation would be fine. So it says graph the two equations on graph paper. What I'm going to do is use Desmos. So let's get Desmos over here. And I have another graph here, a fresh graph. So I'm going to put in here 4.5x plus 56. So that is the position of the tourist. And notice that I'm using x and y here for the input and output variables instead of x and t as I am in my work. And that's perfectly fine. That's just because Desmos can't tell the difference. I'm going to need to scale out in order to see this picture here. So we're seeing that the person starts at 56 meters and is moving away from the origin. Technically, what you could do is just include for x is greater than 0, and the way you do that is to use curly brackets here, braces. So curly braces here, x is greater than 0, and you can see that the graph begins only at time equals 0. We don't care what happens before time equals 0, we know that's where it starts. And we can do the same thing here for the bear. Here's y equals 8x, and that is the graph of the bear. We can see that the bear starts at the origin, which we expected here, and him and the tourist meet up at some point later, and we can see the answer. And I will also do the same. I will limit the x value from 0. So that we don't deal with a time less than 0. So we can see they're intersecting. What I'm going to do is adjust the axes. This is okay if you're new at this, but ideally what we do, and this is so that you know when you're looking at graphs and creating graphs, when you're looking at books, what we do is we take the part of the graph that is interest and make it fill the graph. So I want to cut off these parts here. So what I'm going to do is I'm going to make the x-axis shorter and I'm going to make the y-axis shorter. And how I'm going to do that is I'm going to go over to this wrench in the corner, on the top right corner, graph settings. And you can see down here there's a bunch of graph settings in here. You can change it to be more bold or whatever you want to do there. You can take minor axes or axes numbers on and off. You could take the grid totally out. I'm not sure what that does. But anyway, I'm going to change my axes. So because I'm not dealing with negative time. I'm just going to put negative 10 in here. That seems fine. And then I'm going to go up to, what's a good time here? Maybe 20 seconds? 20 seconds seems to be good. I might even take the x down to 1, maybe. Just 1. So you can see that the x graph, the scale of the x fills up the horizontal direction of this graph. The other thing I'm going to do is adjust the y. It seemed like 128 was the number, so let's do this. I'm going to go maybe negative 10 here and then go up to 150. And that's pretty good. You can see how the two lines fill this graph. And you can see the intercepts here for both of them. Both of the intercepts are here. We can see that they both have a positive slope and they meet at some point. And I'm actually going to back up a step here. Am I? I want to scroll out maybe just a little bit so that I can see the graph a little bit more in perspective. So maybe that's good, okay? So there's the graph of our two lines. We see that they're going to meet at 16,128. So we already kind of know the answer to our problem. It says algebraically solve for the amount of time the tourist has before the bear catches up to them. Okay, this is algebraically. It's not do the graph and look at the graph and be done. It says algebraically solve. So we need to use some algebra in order to solve. So what we're going to do is notice that when they meet, when the bear and the tourist meet, they're at the same location. So that means these two equations that I developed for the bear and the tourist are going to be equal to one another. So I'm going to set x for the tourist equal x to the bear. And I can do the algebra here. 4.5t plus 56 equals 8t. I'm going to subtract 4.5 on each side, so I get 56 equals 3.5t, and the time will equal 56 divided by 3.5. And when we run this through the calculator, just so that we double check, 56 divided by 3.5 is 16. So when I get this answer, 16 seconds, I can go over to my graph and note that that is the time here, right? The input variable is the time and it says 16. So clearly indicate their intersection point on your graph. So I've done that. I've clicked on it. Notice that I'm not putting it in over on the left side and labeling it. That's not verifying what your answer is. You do your answer algebraically and get your algebraic answer, and then you use the technology to do the calculation and get an independent verification of your answer. Not a replication. If you plug your point in and you label it, you're just simply co-signing your own wrong answer if you have a wrong answer. Your equations could be wrong, and you do something wrong here and you get a wrong answer, and it looks right to you, but the calculator is not verifying your answer. You need another independent calculation in order to verify your answer. One last thing I wanted to cover here is maybe there might be another part of the question that says, where is the bear at 5 seconds? Right? So what is the position of the bear at 5 seconds? And you can calculate that. The bear follows the equation 8t. We wrote that up top here. The bear follows the equation 8t. So we can plug in what we know, 8 times 5, which equals 40 meters. Okay, so at 5 seconds we know the bear. Algebraically, we've solved for the bear being at 40 meters. You would be asked to verify this. If I verify this on the graph, what I'm going to do is plug in this input value. I'm going to create a line at the input equals 5 seconds. Okay, so when I go to the graph here, I'm going to create a line. I'm going to create a vertical line at time equals 5 seconds. In this situation, x is my input value, so x equals 5, so that represents when the time equals 5. When the time equals 5, we can see the bear is at 40 meters. So if you were verifying this solution, so this is what I'm saying, if you're verifying this solution, in order to find an intersection point, you're going to create a vertical line, and see how I've done that here. We know then the person's at 78.5, and you could calculate that value. So when you're verifying solutions, it's not adequate enough just to label the solution that you calculated. You must get an independent calculation from the technology that you're using.